Hello, welcome back. So we start the afternoon session with Sachin Jain, who will be talking about scattering amplitudes in Chern-Simons matter theory.
Thank you very much for inviting me to this conference. It's a ADS safety conference. So it's a one version of ADS safety is that I'll be mostly focusing on is Vassiliev-Chern-Simons matter duality. So it's a duality field theory in 3 dimensions, and it's one high dimensional theory, high spin theory. This duality was proposed. This duality was proposed between some high spin theory in one high dimension than this field theory. But later on, it was understood that based on properties of this Vassiliev theory, there is some duality between just the Chern-Simons matter theories. So in my talk, what I'll be focused on only this part and the dualities and various aspects of this theory, Chern-Simons matter theories. And one of the things that I'll be focusing on mostly is the scattering matrix computation. And the question that I'll be asking is that in this theory, can I compute all possible scattering amplitude at large n? By all possible scattering amplitude, I mean arbitrary m to n at all loop. That's the question that I'll be asking. Okay. So, so here I have listed some of the theories that we have studied. So here I have Chern-Simons theory, Chern-Simons gauge field coupled with fermion, which is in fundamental representation. So here all the matter fields will always be in the fundamental representation. So similarly, I have a bosonic theory which is also in the fundamental representation. And the Chern-Simons matter theory duality says that these two theories are dual to each other, provided you take the critical limit in the bosonic theory. By that I mean you compute some physical quantities such as partition function or say scattering amplitude. Under suitable parameter change, you can map the results here to the results here. Okay? Similarly, this duality was further generalized in the case of supersymmetry. And here is an example where I have boson plus fermion, and this is n is equal to 1 supersymmetric theory with one parameter other than Chern-Simons coupling K and SUN gauge field N. I have another parameter W. So this theory turns out to be self-dual in the sense that if I make a duality transformation, physical quantity, as I said, will be will be self-dual. One particular class of this theory which will be of most interest to my talk would be n is equal to 2 supersymmetric theories, and where if I set this parameter W to 1, it enhanced n is equal to 1 supersymmetry enhances to n is equal to 2 supersymmetry. Okay, and here another class of theory where you can compute stuff is you take Chern-Simons theory with boson and fermion and add all possible renormalizable coupling, and it turns out that even with those most general Lagrangian, you can actually compute various quantities. As I'll tell you a little later. So, so here we'll be taking larger limit. So n goes to infinity. Kappa is the Chern-Simons level. That is also taken to infinity, keeping n by kappa, which is lambda, fluid coupling lambda, is kept fixed. So, and the duality that I talked about, where these two theory map to each other, is a duality where kappa goes to minus kappa and lambda goes to lambda minus sine lambda, where my lambda goes from 0 to 1 in the normalization that I am using. So, lambda is equal to 0 is the no interaction, and lambda is equal to 1 is a strong coupling limit. Okay, and for this theory, for n is equal to 1 theory, this W, there is a map, W prime goes to 3 minus W by 1 plus W. So under this map, and with this theory becomes self-dual. Okay, and for this theory, there is no W. As you can see, if I say W is equal to 1, it's a self-dual point. W prime is equal to W is equal to W is equal to 1. Okay, for n is equal to 2, it's a self-dual point. for the class of theory 5, where I have all possible renormalizable interaction, here actually the duality map is much more complicated, and the parameter map is quite non-linear and very complicated. Okay. So some of the things that we noticed while computing this stuff is that at large n, physics quantities such as partition function, scattering matrix, which will be my main aim in this talk, is exactly computable. So this we did for 2 to 2 scattering. Number 2, what we noticed was to preserve unitarity, we needed to modify the crossing symmetry in scattering amplitude, in 2 to 2 scattering amplitude. And that was needed because matter, which is in fundamental representation, say a fermion or the boson, coupled with Chern-Simons, they start behaving like anyons. And then we needed to account for that fact, we needed to modify the crossing relation. So by modify crossing relation, what I mean is that it's not usual that I take S-channel, T-channel answer, do appropriate change of the variable of the S2U variable, I get the, say, S-channel answer. We needed to multiply with some factors, prefactors, to get this thing work. And number third fact would be n is equal to 2 supersymmetric theory, which is this theory. Here, 2 to 2 scattering is non-renormalized, tree-level exact. So if you do the computation here, for n is equal to 1, results are extremely complicated, but somehow, if you set w is equal to 1, it becomes just tree-level exact, okay? These are the few observations that we made, and what the main part of this talk would be to understand why is it possible to compute this scattering amplitude exactly, and why n is equal to 2 supersymmetric case, why the results are tree-level exact. Okay, this will be the these are the two things that I would like to understand, that I would like to describe, and the other thing that I would like to describe is that is it possible to compute not only 2 to 2, but say I want to compute, say, m to n scattering amplitude at all loop, and that will be the second part of the talk. Okay, so okay, so just to give you a brief overview of the rest of the talk. What you will see that the exact, tree-level exact fact, the fact that for n is equal to 2 theory, scattering amplitude does not get renormalized, follows from basically two facts, is that these are dual superconformal invariants that emerges for this theory, and the fact that it also is somehow IR non-divergent, okay, IR finite, and so we'll explicitly write down the amplitude, and we'll show that this is the case for n is equal to 2. And we would then like to go beyond 2 to 2 scattering and try to understand we would like to go beyond 2 to 2 scattering, and we'll see for exactly for n is equal to 2 theory, at least I can at the level of, at the tree level, I can use BCW recursion relation to go beyond 2 to 2 scattering. And the things that as we go along, we will see that combination of dual superconformal invariance and the conformal invariance which makes it Yangian invariance, probably that will be useful to for us to compute, say, loop level amplitudes rather than directly computing. Those we'll be discussing. I don't have a concrete result yet, but I'll just tell you some of the things that we haven't understood. And so one of the hope in all these things is that not only at the tree level that we get a recursion relation, one of the hope would be to get a recursion relation even at the loop level. So, okay. So let me first start with this case. Why to see how can I understand result that the n is equal to 2 supersymmetric case, tree level, all loop answer is tree level exact. So for that, I'll introduce a variable, spinor helicity variable, where momenta would be, so I'll be working in the massless case, so I can introduce these variables. And the notation would be ij. Okay. So ij contracted, this is the notation that I'll be working. And for n is equal to 2 supersymmetry, let me define q as a supercharge, which is a sum of qi, which I can construct. These are on-cell supercharges. And the scattering amplitude that I'll be interested in, phi 1 at 1, moment of p1, 2. This is a 4-point scattering amplitude that I'll be interested in. So the full answer, all loop answer, just turns out to be, for this n is equal to 2 theory, turns out to be just where Q is a total supercharge I have just said. Okay, this is the full, all loop answer that you can compute explicitly by doing swing addition equation computation, and you can show that this is the full loop, all loop answer that you get. Okay, and this is exactly the same as well. You see there is no function of lambda here, and this is the tree level answer if you just also compute tree level. Sorry? Yeah, so phi is a superfield which has, say, boson and the fermion. These are on-cell superfield. So one thing that you notice is that this fact, up to this fact, is given by the supersymmetry. And you are just n is equal to 2 supersymmetry in 3 dimension implies that the 2 to 2 scattering can be determined up to an unknown function of momenta times times this supersymmetric factor, which accounts for all the other scattering. So all you need to do is to do one computation, and if you do that computation, you choose whatever computation you want to do. So you effect this factor. Sorry. Oh, you can use certain identities to. Yeah, you can use say 3, 4. Okay, so what we are going to do is to rewrite this thing in the dual, in a new set of variables. These are called dual variables. This was introduced in the case of, so I'll use and these are called the, sorry, yeah. Sorry?
Does it take care of the non-planar diagrams?
No, so I'll be always at n goes to infinity limit. Yeah.
If you change, for example, lambda 1 to minus lambda 1, it seems to flip sign.
If I, no, this Q also has some momenta, but that will.
If I change the sign of lambda 2, then it doesn't change. The first factor doesn't change sign, right?
That's right.
So is Q breaking the symmetry between 1 and 2, or?
Just a second. So if I change, say, lambda to minus lambda, I have momentum. I have not thought about it. I'll probably think it a little later. So what I'll do is that I'll do a change of variable from here to this p variable to the x variable and theta variable. And what it was noticed in the case of n is equal to 4 super-Mills or ABGM theory, that these were writing down in this variable, it turns out the amplitude becomes again the conformal invariant, okay, super conformal invariant. And for our case as well, we will see that as I can show you, as I'll show you, that again writing in these variables, amplitude becomes conformal invariant. And if I just write in this variable, so one of the things you want that you would like to check, say under inversion, this factor under inversion, this factor, if I call it f, becomes here. So this factor is not invariant. That's the main contrast between n is equal to 4 or the ABGM case, where because of very high amount of supersymmetry, in 3 dimension I had six factors here, delta 6, because I have n is equal to 6 supersymmetry. This factor, this delta function factor was invariant, and there was no x dependence, okay? So this was one of the reasons why, yeah.
Is there a physical meaning for x?
So
here?
x is just this, that I'm just changing.
I mean, it's just some mathematical.
Yeah.
Okay.
So the point is that if you rewrite your amplitude in this variable, you see that there is a symmetry, which is a conformal symmetry or a super conformal symmetry that emerges. Now I want to use that symmetry to argue things that.
No, but when x goes to, I mean, inversion of x, how does p is affected? How is p affected? Pi alpha beta affected?
So the way you should think, these are the inversion not in the Poisson space, not in the momentum space. These are the inversion in this space. Okay.
Okay.
So it will be a bit complicated, but you can work it out.
I mean, but it doesn't imply
So
anything
it's not
physically.
Symmetry. I'm not. So here I'm not talking about this symmetry here. I'm talking about the. Now I'll be writing down my amplitude in this space x, and here everything is in the x and theta space. And I'll be talking just in the here symmetry in this space. Okay.
Okay.
So in the momentum space as well, there is a conformal invariance, and the point is that that invariance and this thing, they do not commute each other, and they form a Youngian algebra that you can use. Okay. So now if you do so. All here I wanted to comment is that the fact that this factor is not invariant, which was earlier thought to be necessary to have dual conformal invariance. But suppose, the factors that is coming here, that actually compensate for some of the fact. And what you can show is that k alpha beta acting on A4 is so this 4-point amplitude has this symmetry, okay? Sorry? K is a spatial conformal transformation and in the X space. So I now, what I'll be doing is that I'll be writing everything in the X space. So K is in the X space. I'll also do analogous supersymmetric thing in the theta and the X space. And I'll find out that this amplitude is dual superconformal invariant with some particular weights of the delta of the external particle, which are delta turn out to be 1 minus 1, 1 minus 1. Okay? So just to summarize this part of the computation, all I have shown that given this result, this becomes a dual conformal invariant with external particles having weight 1 minus 1, 1 minus 1, okay? Sorry? X5 is just, I have introduced a variable. This you should identify with x1. Yeah, yeah.
Sorry, I'm just confused with the notation.
So I have introduced a notation that p4 is equal to, say, x4 minus x5, which is same as x1 by the delta function.
Oh, x5 is same as x1?
Yeah, in the amplitude.
Okay.
Yeah. Sorry?
Inside that square root, what do you have?
x1 comma 3, which is the same as xi comma j, xi minus xj square.
Okay.
Okay, so now, given this fact, I want to check that, now I want to use this, all I have shown you that the amplitude has this dual superconformal invariance. I want to ask, suppose I want to take two assumptions. Suppose my full amplitude has dual superconformal invariance. Can this be used? Can this fix the fully momentum dependence on the amplitude or not? Okay, this is the question. Basically, I'm reversing the. Suppose I had not known that it has this dual superconformal invariance. I just asked that suppose I assume my amplitude has dual superconformal invariance. What does it give? So basically, what it gives, I'll assume. It's a 4-point function with some. What I want to understand, this has a 4-point function is in this dual space with some operator theta, which has some particular weight, as I have written down there. So it will take the form just by the conformal invariance in the X space. Okay, so this I have just used the fact that the 4-point function, if it is a conformal invariant theory, then it can be fixed up to some function of f, which is a function of cross ratios. Okay. Now, if I use these deltas that I have written down here, I'll reproduce exactly this factor. Okay. Sorry, there is a half factor here. I'll reproduce this factor. So, then this full factor gives me the overall function of momenta that I have. Now I have to argue that at loop level, this should not be a function of cross ratios. Okay, this is all. That's the second thing that I need to argue. So for that, I just write down what are the cross ratios. Cross ratios are x12 square. Now, if I look at x12 is nothing but p1, okay, by this definition. That by the definition, x1, so x12 is x1 minus x2, so x1 minus x2 is just p1. Similarly, I can write down this u in terms of I have p1 square, this is p3 square. In the denominator, I have x13, so I can write down p1 minus p3 or plus p3 square, and similarly here, and here I can write down p4 square, p2 square in the denominator. Now, in the case of massless particle, p1 square by on-cell condition, this is 0, and v also by massless particle, p2 square is 0. So all I get is u is equal to 0 as well as v is equal to 0. Okay. So what I'm restricted to, instead of function of uv, sorry, here I could have allowed for a function of lambda, coupling constant, uv I can set it to 0. So all I'll be just restricted to is a function of lambda. Okay. So what I see is that dual superconformal invariance at least fixes the momentum dependence. All I need to fix is the coupling constant dependence, which I tried to fix it by using various facts that these theories are self-dual, and this theory has parity invariance, and the fact of unitarity. So I could not completely fix f of lambda, but we got some restrictions which were consistent with the result. And one more suggestion was that probably I can always redefine my coupling constant to call it as kappa. Okay. So, what I wanted to argue here that the momentum dependence is, if I assume that my amplitude is dual superconformal invariant up to all loop, it becomes tree level momentum dependence. Okay. And this is what the point 3 that I wanted to emphasize here. Yeah.
Sorry. So in this argument, you have assumed these deltas. Is that right? That how
Here it came out. Here it came out of the computation.
Yeah, but in the argument to fix the momentum dependence.
Yeah.
You have taken the deltas as the input.
Yeah, I have taken this deltas as the input.
So how do you know that deltas don't get corrected in lambda? There's no like some another dimension or something. I do not know, but is that obvious?
At least if you construct say 5 or 5, those kind of operator, they all those operators, they get corrected only at 1 over kappa. So that will not, even if it gets corrected 1 over kappa, our amplitude will not see all those things. So I don't have a argument why they are not corrected.
So that is an input?
That's an input.
Can I say that's an input?
Delta does not get corrected. And this second input is that my answer is all loop. It has dual superconformal invariance at all loop. Okay. Okay, so now what I would like to do is, till now what I have understood is that 2 to 2 scattering in n is equal to 2 theory, I have a 2 to 2 exact answer, and also in other theories, I want to ask if is it possible to go beyond 2 to 2 scattering and say higher point scattering, okay? So, before going to the loop level, first question that I would ask is about the tree level. And tree level, one of the things that usual thing is to use BCW recursion relation to construct higher point amplitude in terms of lower point amplitude. And here, the way to do it, suppose I have some arbitrary endpoint amplitude. I take one of the standard ways is that deform two of the momenta by some complex variable, call it z, make them a function of complex variable z. And do the deformation, and if your amplitude has a nice asymptotic properties, then you can use BCW recursion relation. It turns out that except for this n is equal to 2 supersymmetric theories, these other do not have this nice asymptotic follow-up behavior. Okay, so I'll confine myself to n is equal to 2 supersymmetric theories. The basic reason why n is equal to 2 theory has this nice asymptotic follow-up because of the following 4-point function cancellation. So this is bosonic line, this is fermionic line. The coupling constant here, this particular vertex 5 or 5 cyber cyber vertex that get cancels with the gauge field. So this cancellation was very important to have BCW construction at infinity. So I won't go into the computational details, but basically what you can do, you can use supersymmetric BCW result where what you do is that not only deform the momenta, but you also deform the super variables, these theta variables, just to preserve the supersymmetry. Okay, so you deform momenta as well as the super variables. When put this together, what you can show is that this can be written as some lower point amplitude cross some lower point amplitude, okay, sum over I. So here I is the various intermediate channels that can appear. Yeah. Yeah. So what happens is that you suppose, for example, you take a amplitude psi bar phi, phi bar psi, phi bar phi. Okay. Now you draw all possible diagrams that are there. Now suppose you deform the momenta here and here. Okay. What you will see that so you deform your momenta, P make it a function of Z, and what you want to take Z goes to infinity limit. Okay. In that limit, it turns out that the kind of diagram that will appear in computing 6-point function will be of this kind of diagram. Okay. And in the Z goes to infinite limit, you would see that if you there has to be a cancellation between this diagram and this diagram in order to have finite good behavior at infinity. Okay. So that is basically the cancellation. Okay, so here what I have got is the BCW recursion relation for higher point tree level amplitude, and the question that I would like to ask, is it possible to get recursion relation for even for the loop level amplitude or not? Okay, this is a question that I would like to ask. Okay, before going to there, I'd like to point out one more thing, is that in the case of fermion coupled to Chern-Simons, there was no BCW recursion relation does not work. However, what you can do is that using this supersymmetric result, so let me emphasize this point. Suppose you are at the tree level, 6-point amplitude level, then suppose all the external legs are fermion, then what you can show, in the intermediate line, there will be only gauge field and the fermion, those are exchanged. And the contribution will exactly come from this Lagrangian, okay? Although I'm computing in N is equal to 2 supersymmetric theory, for tree level 6-point amplitude, there will be no contribution coming from this or this kind of terms. Only thing that will come contribution from is Chern-Simons with fermion, which is exactly this theory. And using the second fact that you can use is that at the 4-point function level, as I have argued here, there is only one function which determines rest of the amplitude. So that function you can determine using 2-to-2 scattering of the fermion. So using these two facts, you can show that even in the case of fermion, you can get a BCW recursion relation. Okay, just using the fact that you have a recursion relation in the supersymmetric theory. Okay, so now what I would like to do is to ask the same question. Is it possible that there is a dual superconformal invariance or at the higher point function level? So let me start with the 6-point function. So in the case of 6-point function, suppose I have 1, 2, 3. Suppose I deform the momenta 1 and 2. There will be 2 channels of scattering. Okay. So what I have done is that I have written a supersymmetric amplitude where I have deformed 1 and 2. Here I am showing the 2 different Biseidolu channels. So these are the 2. These are the 2 different Biseidolu channels at the 6-point function level. And I want to ask, given the fact that 2 to 2 scattering has a dual superconfine invariance, does it imply that the 6-point function also has dual superconfine invariance or not? So it turns out that this part of the amplitude you can show that it has dual superconfine variance, but it's not clear that the full part of the amplitude has dual superconfine variance under same set of variables. So what I wanted to argue here is that although 2 to 2 scattering has this dual superconfine variance, it's not clear that the higher point amplitude also have this dual superconfine variance. So this part we are checking at this stage. It might turn out to be the case, but suppose you ask the same question that we asked in the case of 2 to 2 scattering. That suppose 6-point function is a dual superconfine variant. Can it fix can it fix the loop momenta, loop amplitude as well or not? It turns out that the dual superconfine variance at the higher point function level is not that powerful enough to fix the amplitude completely. So you at the end of, in the case of 4-point function, we saw that the cross ratios vanishes, but in the case of higher point function, all the cross ratios will not vanish. So there will be some complicated functions of the cross ratios which will remain. So tree level answer will not be the exact answer at the all loop if there exists this dual superconfine invariance. Okay, so we want to tackle this problem in a little different way rather than going to symmetry way. So for that, let me focus on the 6-point amplitude in the case of boson. Okay, here, and what I'll be giving you is how to compute a 6-point all loop amplitude here. Okay, without. So this computation that I'm going to talk now is under, we are currently doing, but I'll tell you what is the way we are thinking about it. So for the 6-point function, let me first draw what are the one loop amplitude that I can draw. So one loop amplitude that I can draw is this kind of amplitude, or this. So here I'm considering, say, a bosonic case. All my particles are external particles are boson, and these are the different kind of amplitude that I can construct. These amplitudes are not 1 pi diagrams, so I can forget about them. These amplitudes are 1 over n suppressed compared to this amplitude. Let me show you how. So at the tree level, the kind of diagram that I'll be interested in this. And this gauge field vertex, gauge field propagator comes with a factor of 1 over kappa. So this diagram at a large n goes as 1 over kappa square, which k goes to infinity, which is like 1 over n square. Here I have three gauge fields, so 1 over k cube. And then there is a one loop here, so it gives me n, so it's also 1 over kappa square, effective order. But you can draw the double line notation here is the following. There is no loop here, okay, in this diagram. So I can forget about this kind of diagram, and it will be very important for our case that this kind of diagram do not contribute. Okay, so the only kind of diagram that I'll be needing to concentrate is this kind of diagram. Okay. Now, suppose I want to go to the all loop level. All I need to do is to add up various contribution here. So kind of diagram that I need to compute are this kind of diagram, say, for example. And this I'll write as the following diagram. Okay? Where what I have done is that I have replaced the 6-point amplitude. Here I have the computation that I need to do is these are the exact 4-point amplitude. These are all exact 4-point amplitude. All I need to do is to take exact 4-point amplitude and compute this kind of diagram. And kind of correction that you can think about, this gauge field correction that it can come, you can always reabsorb it in this exact 4-point function. So all you need to do is the computation of this diagram at the 6-point function level. And some combination of this. So these are the two only non-trivial diagrams that you need to compute. And these are exact 4-point amplitude. Those are already known. Okay, which is a quite straightforward computation one can do and get the exact 6-point function. For the case of n is equal to 2 supersymmetry of the fermion, I don't have this kind of diagram. I only have this diagram, which is readily computable. Okay. So this tells me how to compute 6-point function. Up to all loop exact. I want to go beyond 6-point and I want to go to n point, okay? Okay, so to do that, it turns out that n-point computation is a bit more, say, 8-point computation a little more involved. It's not, I can compute in the following way, same way I just argued here. But this kind of diagrams are a little hard compared to this kind of diagram to compute. So at this stage, I'm going to take a little different route. So I want to build an intuition about the higher point function at the loop level. So to do that, rather than going for all loop, I'll first try to understand what happens at the one loop. Okay. So what I want to understand is that can I compute n-point function at one loop? And hopefully I'll be able to get some kind of intuition to go from one loop to the all loop, or probably I'll be able to get, say, some kind of recursion relation. So way to do is following. Let me start with first 2-to-2 scattering, 4-point amplitude. And then I'll go to higher point amplitude. Say 2-to-2 scattering, I'm interested in the bosonic theory at one loop. So kind of diagram that I need to consider are this. Permutation of these diagrams. And permutation of this diagram. So these are the all possible one loop diagram that I can write down. So way to compute this would be I'll use the cut construction method to compute this. And just looking at, because these are Chern-Simons gauge field, if I cut any of the gauge field leg, I'll get 0. You can check this explicitly. So the only non-trivial cut that is allowed in this whole diagram is this cut, okay? And you can immediately write down the answer that it will be proportional to the bubble diagram, okay? This is the full answer, and you can do a computation to check this, okay? Now suppose I make it supersymmetric. In the case of supersymmetry, you can show that even the bubble diagram vanishes, which is consistent with our result that the for supersymmetric case there is no scattering amplitude do not get renormalized. Okay. Now, what I want to do is to go to higher point function. Let me start with the 6-point function, then I'll go to higher point function at one loop. So 6-point function, suppose I have this kind of diagram there is a theorem the theorem. It says there was a paper, beautiful paper around 1983 or something, which said that suppose you are in d dimension, there cannot be more than a d number of denominator in the loop integration. Okay, so what does it immediately say is that suppose I'm interested in 6-point amplitude, 1, 2, 3, 4, 5, 6. This would maximum be given by a triangle diagram in the cut, and then it will be given by bubble. This is it. All I need to do is to compute these coefficients. Okay, and these are not at all difficult computation to do. And the basic point is that even if you have 6-point function in 3 dimension, I can have maximum 3 triangle diagram. I cannot have a box diagram. Okay, so even if I increase here number of legs, I can always rewrite things in terms of these 2 bases. And for the supersymmetric case, this term actually vanishes. So all I'll be left with is computation of this, which is not very difficult. So we are currently doing this computation, and what we hope is to learn some lessons, such as probably there will be some recursion relation at one loop, or probably for n is equal to true theory, it might turn out that the one loop result is just 0, which we have not yet done. We have done for the bosonic case. So the hope is that probably at the loop level, just like the tree level, we had some recursion relation, we would be able to get some recursion relation. If not, we'll see how to do. Okay. Yeah.
It does not renormalize, the second diagram you said that it won't contribute because the amplitude cannot be, won't get renormalized in supersymmetric theory, n equal to 2.
That is only for 2 to 2 scattering. For 2 to 2 scattering, you can show a coefficient of this thing vanishes. But for higher, we do not know, but probably they vanish, I don't know.
So I wanted to understand this n equal to 1 and n equal to 2 actions that you have written down. So these fields, psi and phi, they're part of a multiplet, or?
Yeah, chiral multiplet.
So they're the same for n equal to 1, you have the same, and n equal to 2, you have the same?
Yeah.
Okay. So it's not like you're truncating or something? It's like you have the same field content for the...
Yeah, I have the same field content.
For the n equal to 2 multiplet as well as the n equal to 1 multiplet?
Yeah, so only thing is that you have this parameter, which is the superpotential something, which is you are fixing probably. But they have the same, that you have Chern-Simons with one chiral, one chiral multiplet.
Okay. So you don't have any, like if you want to write them as a super field,
yeah.
So the superspace coordinates will have one index I for n equal to 2. So that index I doesn't appear in any of the fields.
Sorry, what do you mean? So here, all I worked with, all I needed was the on-cell superfield formalism. So those things has, so the thing that I did was they had indeed, like as you say, so they had 2 indices. Yeah. But we do not have an on-cell formulation for n is equal to 1. For n is equal to 2, we do have an on-cell formulation, but for n is equal to 1, we do have an on-cell formulation, but for n is equal to 2, it is little different. It is, for n is equal to 2, we deal with a little different compared to n is equal to 1.
Okay, so the only reason I see why you call it n equal to 2 is that this has 2 supercharges.
Yeah. So at that particular value, I have
the particular value of this W.
Yeah.
Two conserved supercharges.
Yeah.
Okay. Okay.
Any other questions, comments? If there are no further questions, let's thank Sachin again.